Assalamu alaikum wa rahmatullahi wa barakatuh. This is our third lecture in explaining the basic concepts that you need before proceeding to computational chemistry. In this lecture, we will speak about the wave function, basis set, and different model for computational chemistry. So let's start with the first concept that we will explain is basis set. Basis set is a mathematical equation is used to explain the wave function of the atomic orbital, and later on it will be used to construct the molecular orbital. So before we proceed with the basis set, I would like to remind you with the atomic orbital for the simplest atom, which is the hydrogen atom. The atomic orbital in the first shell is 1s, which is a sphere. In the second shell, you have two types, 2s and 2b. In any shell, you have n-1 node. So the 2s and 2b, both of them has one node, but in the 1s, there is no node because n-1 equal to 0. In 2s and 2b, there is one node. The 2s has the node in the radial part, and the 2b has the node in the angular part. This means 2s is actually two spheres inside each other. As you can see, blue and yellow, blue and yellow. Between these two, you will have a nodal plane in the shape of a sphere. The 3s, of course, will have two nodes. So it is actually three spheres inside each other. The 4s will have three nodes. So it is, as you can see, more spheres inside each other. The 2b orbital, if you move in this direction, the number of nodes in the radial part are the same, while the number of the angular part node increase. That's why the s orbital in the b orbitals become like two loops. Why? If you take a sphere and you split it in two, it becomes two loops. And then if you split it again in two, it becomes four loops, which is D. If you split it again, it will become 8 loops. So when you move from S to B, you get 2 loops. From B to D, you get 4 loops. From D to F, you get 8 loops because you are splitting it in the radial, in the angular part. So what's the difference between 2B and 3B? As you can see, the one loop here has 2 loops inside each other, has 2 spheres inside each other. The same story happened in the 2S, where 2 spheres inside each other. Here, 2 loops inside each other because you have an extra node in the radial part. This is a simple way to explain the atomic orbital of hydrogen. The same where applies for hydrogen apply to all atoms. The difference between one atom and another atom is the Z effective, or the amount of nuclear charge that reach to that electron in the outer orbital. The Z effective is a summation of the nuclear charge minus sigma, which is the shielding, or better to say, which is the repulsion of other electron to this electron. We will explain this later, but in basic concept, you just don't need to know that all atomic orbital we are using in computational chemistry is based on the same concept. They are assuming that they are the same as the hydrogen atom, without just changing the Z effective and some special parameters. So if we move on, how to explain such atomic orbital in numerical way. To explain it in a numerical way, you need some basis set. There are two main basic type of basis set. One is localized using Gaussian function, and one which is delocalized using either real space or plane wave, where the difference between the two is just this one is depending on the momentum and this one is just not like this. This delocalized one will not be discussed in details in our lecture because they are related to the periodic structure or bulk material, surface, whatever. But localized one is good to explaining molecules where they are localized or centered on the atom itself. There are actually many types. The common types that we usually use, the Dunning correlation consistent, or sometimes it is augmented with diffused function, and the effective core potential. The common type which you usually find is divided into the minimal and split valency or Pople type. So let's go in further details. What's the meaning of this? The actual atomic orbital is a slater type orbital, which is a function of exponential minus constant as a function of radius r, or the distance from nuclei. The Gaussian function, which is exponential minus constant to r square, is quite similar to it. If we draw the slater type orbital, which is very similar to the hydrogen orbital, and the Gaussian function, you can see they are kind of similar. But the slater type orbital, or the orbital which explains the atomic orbital, is difficult to solve. The Gaussian type orbital is more easy to solve from the numerical way of thinking. So we will use the Gaussian type orbital, which is a different function than the real slater type function, to explain it. But as you can see, there are some differences. They are only equal in some points, but as you go far from these points, they are different. So this point is one atomic unit, which is, the radius of, interaction between atoms. So it may be good in the range of atom interaction, but not good near to the nucleus, not good for far distance. So in this way, we want to say that we are not using the real S-type orbital, slater type orbital, that usually explains the atomic orbital of the hydrogen more accurately, but we will use, instead of them, some other easier Gaussian function, easy to solve, but not real. So how to solve the problem of that are not equal exactly to the real one? This is what happens if you use the minimal basis set. The slater, will we think that of a slater as a real one, and then we'll try to fit it with one Gaussian function, or two Gaussian function, or three Gaussian function, which means we will make a summation of three Gaussian function or two Gaussian function to construct one atomic orbital. If you use one slater type, the difference is big, as we saw in the previous slide. But if you make them large, if you increase the number of Gaussian required to express one slater type orbital, the simulation becomes better. The range for for them to become equal becomes better. As you can see, three Gaussian function gives a very wide range for for similarity between the slater type orbital and for the Gaussian function. So one Gaussian function is a very small minimal basis set, and two Gaussian, three Gaussian, expressing one slater type orbital with some Gaussian function is called minimal basis set. The minimal basis set use only the occupied orbital. Any occupied orbital, you just express it with number of Gaussian function, either 1, 2, 3, 4, whatever. And for every slater type orbital, there are some Gaussian function required to explain. As you can see, 3 is very good, 1 is very rough, and more than 3 will be kind of unnecessary, because the difference is, will be good to explain this part, which is there is no electronic character in that very near to nuclei, and this part is far from nuclei. So we only interested in in this part. So the 3G is just enough to explain this part very good. There are one example for the minimal basis set is STO 3G and formaldehyde. Formaldehyde is composed of 2 hydrogen atom, 1 carbon, and 1 oxygen. The primitives is for, let's see how many atomic orbital in H is 1. We have only 1 S. In the carbon, we have 2 S and 1 B. Here the 2 means 2 of S orbitals, 1 S and 2 S. He means the number of S orbitals. So we have 2 S orbitals and 1 B orbital, which is the 2B. Of course, there is no 1B. It means 1 of the B orbitals, the number of the B orbitals, and 2 of S orbitals in carbon. In oxygen is the same, because oxygen also has 1 S, 2 S, and 2 B. So 2 S orbitals and 1 of B orbitals. For every of these orbital, you will use 3 Gaussian function to explain it. 3 Gaussian function to explain it. So for 1 S orbital, you need 3 Gaussian function. And for every B orbital, you need 3 Gaussian function, and so on. So in this case, how many atomic orbital you have? 1, 2, 3, 4, 5, 6. And this one is a 3 orbital. This one is a 3 orbital. So another 6. 6 plus 6 is 12. So you have 12 atomic orbital in the formaldehyde. For each of these atomic orbital, you will get 3 Gaussian function to explain it. So you need 36 primitive Gaussian or 36 Gaussian function to explain this atomic orbital. This is a minimal basis set with acceptable, representation. As we saw, the 1G and 2G is not good. Another way is to think about it in a split valency basis set. What's the meaning of split? Split, simply think about that the atomic orbital are not of the same value, not of the same importance. There are some core inner orbitals, and there are some valency orbital, and also there are some, empty orbital which will share in some reactions. So if we consider them in different number of Gaussian function, then we care so much about the inner one and less for the valency one, and much less for the empty one, because they are empty, their expression in a more accuracy maybe not that important. This is called split valency. So you divide the atomic orbital in types, in 3 types. The inner, and express every one of the inner orbitals or the core shell orbital with the 3 Gaussian function, the valency one with 2 Gaussian function, the empty one or the virtual with 1 Gaussian function. If you add one more, means add another empty orbital of the same type. Means, for example, if you speak about carbon atom and you speak about 631G, this means the carbon atom has 1s, 2s, 2b, which means 1 in the core orbital, which is 1s, and 2 in the valency, which is s and b, which are 4 valency orbital. This is 1, this is 3. And the 1 means add 1 of the similar type as empty, which is 3s and 3b. Same type as in the valency one. If the valency has s, so you add s. If the valency has s and b, you add s and b. Similar type. So every one, if you add another one, you add 4s and 4p. So you have 1 core, 4 valency, and 4 empty. For the core, you will express it in 6 primitive Gaussian. For the valency, you express it in 3. And for every empty, you are using only 1. So we have 4 multiplied by 3 is 12. 1 multiplied by 6 is 6. 4 multiplied by 1 is 4. This is the number of primitive Gaussian. If you sum all of them, you get 22 primitive Gaussian needed to express the 9 atomic orbital or the 9 basis function in the carbon atom. Note the same for all elements in the second period. I mean, if you use oxygen, nitrogen, all of them in the second series, all of them will have the same number of primitive Gaussian to express the same 9 basis function. For hydrogen, the story is quite different because hydrogen has 1 s1. It has no core electrons. So if you divide the atomic orbital in types, you will get 1s, which is the valency. And if you want to add 1 empty orbital, you need to add it with the same type that is in the valency. The valency has s orbital only, so the empty will have also s orbital only. So you add 2s as an empty orbital. So you have 2 orbitals, 1s and 2s to express the hydrogen atom. There are different more types of basis set, like double zeta and triple zeta. Double zeta is just like double, means 2 types, 2 sizes. Like if the hydrogen is 1s, the double size will be 1s and 1s and 2s. The triple size will be 1s and another 1s and another 1s. So you see the electronic configuration. If you double the set, make it double, then it becomes double zeta. If you make it triple, that becomes triple zeta. We will not go in details in such basis set. There are different ways of changing the basis set, which is called polarization. Polarization is to add a new type. As we saw before, when you add an empty orbital, you just add the same type that was in the valency orbital. But if you add for the hydrogen atom, if you add p orbitals also, which is not existing in the valency, this is new type. This is called polarization, adding a new type, like adding p orbitals to hydrogen or d orbitals to the atoms of the second row and f orbitals to the transition metal. This is called polarization, adding new type to the empty orbital. usually expressed on star or double star. If you use it for star, you will add it for heavy atoms only. If you use it for double stars, mean you add for the heavy atoms and for the hydrogen. Heavy atom means all the atom rather than hydrogen, all the other atoms rather than hydrogen. So the star means add polarization for all atoms and except hydrogen, and double stars mean add polarization for all atoms, including hydrogen. This is a way to express it, but recently we used a more sophisticated way for expressing it by writing D and B, D, comma B, where D means they add D orbital to the heavy atom, B add B orbital for hydrogen atom, because the new type for hydrogen is what? Is B. New type for, much heavier atom in the second row, S and B, is D. This is usually the polarization function. The diffused function is to add plus or double plus. Plus or double plus means to add an extra S and B orbital. To add an extra S and B orbital to the system. If you use 1 plus, means put the diffused function, which is the S and B, for heavy atom only. If you use double plus, means for heavy atom and hydrogen atom. So if you see double plus means all atoms add to them S and B. If you see 1 plus means only atoms rather than hydrogen add to them an extra S and B orbital. Of course, for S orbital and B orbital, for any empty orbital, you use one Gaussian function to express this. There are different types of basis set called effective core potential. It's usually used for heavy atom like bromine. In this way, we take some orbital and put them as a core or effective core, take them out of the equation to make the equation much easier for us. So we have many ways to express the effective core potential. One of them is a small core, as you can see. We take this part and make it as a core and keep the other electrons active, or large core, which is include all these and leave only 4s and 4b as an active. So it depends on the level, but the idea of effective core is just to take the inner core electron and put them as an effective core, because they will not share in the calculation. Of course, they will affect the energy, but they will not affect the chemical bonds. They are not interacting to make chemical bonds. So in this case, you can express this as a core and you keep it as some kind of fixed wave function in the calculation. So choosing of basis set. Like for example, if you are expressing hydrogen bond, hydrogen plus, hydrogen minus, you better add a B function to the hydrogen to express it better. The diffused function, or adding S and B orbital, usually is good for large interaction. The interaction, far away interaction atoms, weakly bounded states. And double zeta and triple zeta, are good, but is quite heavy for the calculation. So it's good for if you're studying some mechanisms of the reaction. This is double zeta, triple zeta is quite good, but it's quite difficult. Dunning basis set is also a type of basis set that we usually don't use so much. It is a correlation consistent, which means it's embedded inside it with correlation consistent, and B means it's also polarized, and it can be double, triple zeta, quartet zeta, and so on. This is also one type of the basis set. We will not go in details of these basis sets. Now we want to summarize the computational chemistry possible approaches. Computational chemistry, as we saw before, is based on the Schrödinger equation, or electronic structure model. Electronic structure model means calculation related to the electrons. Or it may be, ignore all the electron calculation, no electron to be considered. This type of calculation is a special type in no Schrödinger equation included. It's called molecular mechanics. It's not based on Schrödinger equation at all. This one, is quite different. So all the electronic structure method, or the electron dependent, either to consider all the electron or to consider some of the electron, which is called semi-empirical. The semi-empirical has many types. One of them is the Huckel method, which is using the pi orbitals in the diene or butadiene, conjugated diene, or all the valency electron, which is called extended Huckel theory. So extended Huckel use all the valency electrons, not only the one on sharing in the pi, but the pi and the sigma. And it has many types like sendo, endo, mendo, like complete neglect in, modified neglect of electron correlation, because, here you are simplifying the, electron interaction in a very simple integral, as you know about the model of Huckel theory. This semi-empirical method, as you know, it takes some experimental values or what's called parameterization to parameterized by some calculation. This way makes the calculation much faster, but actually less accurate. We will compare them later. If you consider all the electron and apply Schrodinger equation, you have two possible ways to do this without any approximation, or from the beginning. Ab initio means to take the wave function as it is and make the minimal approximation possible. This called Hartree-Fock calculation. It's actually lack of the energy correlation. If you add energy correlation to it, you will get molar blessed 2 like MB2 or coupled cluster methods. Of course, to do this, you need an extra time. The second way is to make them in the same step, both of them together, but in this way you modify the process. You are not solving the wave function, you are solving what's called the density function or electronic density function. This is the density functional theory. It has many types, but many categories, but simply for simplicity we are saying that it is divided into pure and hybrid methods. So what is molecular mechanics, or the method that's not dependent on the electronic structure? In this case, the energy is just a summation of the change of the bond length from the experimental or the parameterized value, a change of the bond angle from the parameterized or the experimental values. So you need the program manager or the program who makes the programmer need to know the bond angle and bond lengths and dihedral angles for all atoms and have all these database. And the geometry, current geometry, if is different from the the equilibrium or field geometry. Here you need a huge database for all atoms. This is very fast and it's good if the model that you are using is quite near to the parameterized value. The parameterized, as more as the system that you are using is very near to the parameterized value, your result will become very good. Here you are using the bond length, the bond angle, the dihedral angle, and then sometimes the charge on the atoms as some calculation. This is, as you can see, there is no electronic configuration, no electronic calculation are included in such calculation. The electronic based method, if we want to compare the method based on the electronic configuration, the one which uses the Schrodinger equation, as you can see, ab initio 1 is implied in many programs like Gaussian, Spartan games. They evaluate the integral from the first principle with minimal approximation. They are quite slow and they need a decent basis set to get good result. But the result obtained from the ab initio need energy correlation later. Energy is not good, need to be correlated. So you need to do an extra step using MB2, coupled cluster, or whatever. Density functional method, similar to ab initio, but include electron correlation in one step. So energy density is calculated instead of the orbitals. It's not as slow as ab initio. And actually, if you consider ab initio plus some kind of MB2 or correlation method, DFT will become much faster. But the main problem of DFT is that you have many types to select from, so you get confused which one to select. In case of semi-empirical, the semi-empirical method use parameters to evaluate the integral, which is making the calculation quite fast. But the main problem is that some atoms are not available in the calculation. Some atoms are not available in the database. The model chemistry is actually a combination of selecting the method that you are using, either Hartree-Fock, MB2, Israelab, whatever, and the basis set. It is very important to know that for the electronic structure method, especially the Hartree-Fock, the MB2, the coupled cluster, the density function, all the ones that consider all electron in the calculation, this one you need to specify the basis set. You need to specify the basis set. For all other methods, you don't need to specify the basis set. Even though that semi-empirical use some kind of valence electron, but you don't need to specify the basis set. It is automatically embedded in the method. So for all these methods, consider all electron like ab initio, DFT, Hartree-Fock, all the method under the consider all electron, you need to specify the basis set. For other method, you don't need to specify the basis set. The combination of the method and the basis set is called the model chemistry, or the model that you are using for the calculation. Also, you need to specify if the compound is closed shell or open shell, means all the electron paired or some electron unpaired. The combination of these is the model that you are using for the calculation. This is the theoretical model that you are using. As you can see, going from this small model to very large model like Hartree-Fock with no energy correlation, MB2 is quite better. Coupled cluster with triplet state. As you go from here to here, the most accurate model will be full CI with the maximum correlation plus no approximation at the same time. And as you go from here to here, the basis set, minimal basis set, split valency, polarized and diffused, whatever, maximum basis set or complete basis set. As you go from here to here, you are increasing the basis set. As you go from here to here, you are increasing the correlation energy. So the maximum correlation and the maximum basis set or the complete basis set will give you the exact solution or the maximum accurate solution. But to reach this, you need to take a very long time calculation, which is very time consuming process. Actually, it's better to, make some kind of balance between the method and the basis set. So if you select something like this, you better select a medium basis set. If you select a very accurate one, you need to select a very huge basis set. So it's better to make some kind of, for each correlation, if you increase the correlation, it's better to increase the basis set at the same time to make it balanced. This is the end of today's lecture. Thank you for listening and hope you enjoyed it.